Hi, everybody. Hi. I will speak some words about our speaker, Professor Brasser. Professor Brasser is graduated in physics 1971 and telecommunications and electronics 1974 from British University in Brussels, where he also obtained a PhD in physics. He worked in at the Belgian Space Institute and in 1988 joined the National Center for Atmospheric Research, NICAR, in the USA. Talk, and he will talk about climate change and air quality since 1950.
Good afternoon. You must be a bit tired after this very exciting workshop. Some of you have been there 4 days and have still to go a 5th day tomorrow. So I choose to basically relax a little bit and talk to you essentially about the challenges we are facing with climate change. And of course, I'm going to start by showing you a picture that I took 2 weeks ago at the airport of Beijing. Fight climate change, air pollution and climate change are two sides of the same coin. I think it's interesting to see that the Chinese put in the airport today. So policymakers start really to realize that all problems in the Earth systems are related, and that basically the solutions to this problem will require a real transdisciplinary view. So what I'm going to do today, I'm a physical scientist, I'm not a social scientist, but I'm not going to try to put basically the physical science around climate or the chemical science around air quality in a broader Earth system context. Of course, when we look at the climate system in general, and I'm not going to be immediately going to the urban aspect, but in more general, we have to deal with a lot of aspects. The energy cycle in the system, the water cycle in the system, which is closely related. And now, because we are emitting greenhouse gases, we have to deal with the carbon cycle, we have to deal with the nitrogen cycle, and we have to see how they all connect. So ecological, ecological, hydrological, micrometeorology, atmospheric chemistry, biosphere-atmosphere interaction, etc., are essential to understand basically how natural managed ecosystem affect, for example, urban canopies. And here we can talk about issues that are very urban or very disturbing, like fires, floods, drought, and air pollution. Now, if we go a little bit in the history, we will see that climate science has made, in fact, enormous progress in the last centuries. Let's go back 200 years ago, when Fourier, who was in France, here's his picture, he tried to explain an experiment that had been done by Agassiz, a Swiss philosopher who had been going on the top of the Mont Blanc, the mountain in Switzerland, France, and Italy. And Agassiz took with him a box that had 3 levels of glasses and 3 thermometers inside each of the compartment, and realizes that the warmest compartment was the one under the 3 glasses, or the 3 layer of glasses. And Fourier wanted to explain that. And so he realized that maybe the atmosphere was about, not exactly like this, and that the solar radiation was penetrating all the way down to the surface, but that invisible ray energy that was trying to escape the Earth was trapped, just like in this box where it was trapped by the glasses. And that's why we call it greenhouse effect. Now, interestingly, we always forget a woman who played a big role in the beginning. And in particular, this lady called Miss Foote suggested that CO2 is a greenhouse gases because she made experiment with air, with water, with CO2, put radiation on top of it, and find out that the glass that had the container that had CO2 inside was the warmest of them. Later on, Arrhenius, this was around 1900, was very worried, not so much about the warming of the planet, but about the global cooling of the planet. We had before glacial period, and this scientist from Sweden was very worried that ice time could come back, a glacial period could come back, but he had a solution. He said, let's burn the coal that we have in the mine, and if we do that, we will enhance the temperature that will counteract this possible cooling, and in reality, we can, if we double CO2 in the atmosphere, the temperature will increase by about 4 degrees Celsius. So, he was disputed. His theory was not immediately accepted, although Tyndall here measured the absorption of CO2 and the absorption of water. This gentleman from England, who was an engineer, but also had nothing to do with meteorology, but was just interested, he suggested that the increase of CO2 and the increase in temperature that were recorded were probably related, and that there was a greenhouse effect. People called it the calendar effect at one point because he was the person. And then models came in later on. For example, you see here the Nobel Prize man, who kind of used a model to really predict what would happen if you double CO2, and that ended up in what has been called the Charney report in late 1970 and 1975 exactly. That was the first consensus report that climate change could result from the increase in CO2. It's not the first IPCC report, but it's really equivalent. And they gave an estimate of how much the temperature would increase And this was the beginning of a certain consensus of the scientific community. This report really was submitted to the governments, taken seriously into account by industry, who wanted first to do something until changed their mind and said, no, we're not sure about those results. Well, at the same time, of course, the science has evolved in becoming more and more comprehensive. In the mid-70s, climate models were essentially atmospheric models. It was a continuation of what the weather people had been doing. The weather people were trying to forecast weather. Well, if we forecast weather, maybe we can forecast climate. Let's take atmospheric model and run them for a much longer time. Didn't work very well. Well, then they ended the land surface. Then they realized that the ocean was crucial and sea ice in the evolution on the climate, and they started coupling ocean model with atmospheric model. And it went on like that. Sulfur cycle, land carbon, ocean carbon, atmospheric chemistry, dynamic vegetation. And so now we have much more comprehensive models that take into account the physics, the dynamics, the ice aspect, and the biosphere and the biogeochemical aspect. But people started at the same time to realize that the Earth had a system in it that would regulate its evolution. There is a natural Earth system regulation. And that's the system that has maintained the planet habitable for life over a very, very long term of millions of years. And it has been regulated to a large extent by life. So now, in addition to what I just showed you, the physics, the chemistry, the issue of the connection with life become important. Life has been shaped by the planetary environment. And at the same time, the planetary environment has been shaped by life. Earth system regulation is closely linked to nutrient regulation, to oxygen regulation, to carbon regulation, and more generally by temperature regulation or climate regulation. And so the question was really a new way of addressing the problem. Are not human activities able to take these regulation mechanisms, what we call negative feedbacks, by changing them into positive feedback by which basically the planetary operation would go away from their natural, stable evolution? Could we really bring the system out of control, or maybe in another stable system that is very different from the one we know? And now we had to look at the problem in a much broader sense. On the left, you see the physical system in blue, the troposphere, the stratosphere, the ocean, the upper ocean, the lower ocean. All that is included in the physical model. Freshwater, vegetation, cryosphere, the ice. But on the other hand, you have what's more in yellow, the energy system, the knowledge development, the science, the technology, the institution, the political economy. And then looking how all that is moving through production and consumption, that is influenced by culture, by values, by belief. And you see now arrows that are going from the two systems, one into the other. Climate change has an impact on the human system, extension also, but on the other hand, the operation through greenhouse gases and reactive gases emissions are affecting the physical system. So a big, complex system to be addressed, and the science of complexity needs to be here taken into account. This is a bit of an introduction. We have to recognize that this view that is now 20 years old has been taken seriously into account, but that at the same time, we are at a critical point in human history. Our population is increasing, and nobody knows that very much, but our current population, the number of people on Earth today, represents about 7% of the total number of people who have ever lived on Earth. That's a big forcing. The cities have started a long time ago, coincident with domestication of plants and animals, and trying to have the first densely packed houses in certain limited area. Hello?
Yes,
Come on.
trying to see how I can fix. Sorry, I didn't want to interrupt you.
Kidding. What's the problem? Something not working?
Escape? Okay.
And then after you
Ah,
again.
Okay.
so I pushed on something. What should I do now to bring it?
No, no. There. Yeah.
So that's the first, apparently the first city. No. It's my screen. Help. On my screen.
You keep going, and I can.
Like this?
Yeah, because some images higher resolution.
Okay.
It breaks. So you
All
do
right.
this. Don't go.
Good. So development of cities. I showed you one of the first city. This is another one called Paris. In the 18th century, grew around castle, monastery, trade routes. Exploration and expansion started. Industrial revolution came with rapid urbanization, significant growth and challenges, which we're still encountering today. Overcrowding, pollution, poor living condition. Cities developed factories, railways, etc. Urbanization increased, and the landscape is very different than when the first city was established. Agriculture became relatively industrial. You can see here in US, this is in I don't know exactly, at the beginning of the 20th century. And we have to ask ourselves now, how are things going to develop in the future? Well, the world of 2050, which is a bit the topic of my presentation, will be very different. Population will continue to increase for a while, but will probably peak around, some people say 2040, 50, 2070. According to the Club of Rome, in one of the latest studies, the GDP will grow, but more slowly than it's been in the past. The CO2 emission should peak, we'll see, around 2030, 2040. The temperature increase, which has reached already 1.5 degrees, should go beyond 2 degrees. Climate change will probably be limited by the usable of renewable. The plus 2 degrees, the 2 degrees warming will cause probably real difficulties. Planetary ecosystem will suffer, and new costs will explode, in particular to support adaptation and protection against disaster. So between now and 2050, 2060, a lot of changes are expected in the way the planet is organized, in the way the economy functions, and finally, in the way people will be witnessing rapid changes that could be very substantial. So having this as a route in front of us or way forward, we should recognize that we are at a crossroad. And this crossroad that has really triggered attention, favor the need of action and solution, appears today in a context that is also changing. First of all, what do we see? we certainly see inadequate progress on sustainable development goals, including climate action. Just see what happens with CO2 increase. Climate change impact become larger with related losses and damages, and for many people, increase climate anxiety, and that could continue in the future. There is certainly some environmental degradation. COVID-19 pandemic has changed our value and our way of functioning in many respects. The war in Ukraine, the war in the Middle East, regional conflict has changed the mood to many and has put maybe issue of security in front of issues of developing solution for climate change. Growing inequality, nationalism, populism, I don't have to tell you today. There is certainly a declining social cohesion and an increased polarization, and I don't have to tell you that either. There is certainly a disinformation in many respects and an erosion in trust, in the trust of the science, and that's of course a concern for us here as scientists. So in spite of all that, we still have a number of challenges between now and 2050. And I'm going to talk about 5 of them. The first one is that we have to continue to understand the system. So observation, discussion have revealed the complexity of a connected system. That's what I mentioned a bit earlier. So we need to have a more deep and complete understanding of the Earth as a system, and that's needed if we want to prepare society to address and find solution to the system. We need long-term observation, we need skillful model and prediction system. Adaptation planning must include an understanding of complex risk, including weather and climate extremes. The limit of climate predictability is another scientific question. We must establish those limits, and is part, of course, of an early warning system. How long can we predict? Can we predict things that are going to happen in 2 months, 4 months, 6 months in terms of the state of the planet? Risk and impact need to be quantified and uncertainties communicated before adaptation measure can be planned. So that's a way of us to add, as scientists, to add knowledge to the climate problem. And I'm showing you here quickly a number of questions that are related to what I'm doing. And in fact, I'm going to raise 2 or 3 Earth system questions from let's say, physical and biological point of view, essentially. So first of all, we need to better understand planetary feedbacks. And I show you here some of them. Some include the polar region, some include Arctic ice, wetlands, permafrost, and in fact, Amazon rainforest die-off, changing the ocean sink of CO2, which could suddenly amplify the response of the planet. And then also the possibility of release of high methane from the disappearance of some methane hydrate. So there are a lot of these type of questions that we understand superficially, but cannot necessarily quantify and make sure that they are well taken into account in the model. I'll give you an example, another example, which is the methane trend. You see here the methane trend between 1985 or so until now in the lower part. On the right or in the middle, you see methane trend, which was high, decreased, and then has been increasing and is now higher than ever. So what drives this irregular increase in biological methane in particular? How does the methane loss change in time? It's not only the emissions, but also the loss. how is the methane budget affected by anthropogenic emission? And can we start thinking about methane geoengineering, controlling the methane emissions, or at least the methane concentration? That's, of course, a huge question, since geoengineering is not just a scientific problem, it's a societal problem, it's an ethical problem, and I'll say a word about geoengineering a bit later on. Another Earth system question under challenge number 1, are tipping points predictable? So, critical control in the system, if they are exceeded, can lead to significant changes in the state of the system, even though the forcing is limited, is small, but the response is very large and perhaps irreversible. And you have different ones. They are here. Some involve the cryosphere, some involve the biosphere, some involve the circulation of the ocean and also of the atmosphere. Of course, one that is well known is the future of the Amazon here in this region, but you could cite some others, and how well do the models take that into account? These are a nonlinear effect and difficult effect to predict, and there's a lot of debate, even to see if those tipping points are susceptible of happen. Some people say, no, we have never seen anything like this. But for example, for Europe, if the overturning circulation in the Atlantic was to stop, all the world would be warmer, but Europe would be colder. So it could be a very different situation. Another question that I can mention as an Earth system question, how does food production affect the fate of the planet, and how does climate change affect food availability and quality? I think that to a large extent, the future of food for our health, for our well-being, is going to become an increasingly important question, and food will be affected by climate change. Introducing sustainable agriculture and a good forest management becomes an important issue, in particular in relation with climate change. So far for challenge number 1. Let's move to challenge number 2 that the scientific community has to us. And one is to observe and to model. I'm not going to say too much about it, but sustained observation and modeling or understanding are a springboard for climate-informed decision-making, development planning, and climate action. So we need to improve our observing system to monitor the future of the planet. We need to improve our forecasting tool, and we need to develop a climate information system, not just for a few climate scientists, but for every citizen in the planet, with open access and data sharing, which is a big political issue between the nations who might not want to share information. By the way, the use of technology should be adopted for the benefit of the citizen. You know, we went really through 3 soft revolution or quiet revolution. The first one is the quiet weather forecast revolution. You know, around 1980, the weather forecast success increased dramatically because we had access to a number of new technologies, satellite, computers, and others. The digital revolution came in, which also improved very much the dispersion of information, and today we have machine learning revolution. So we will soon be able to have 1 kilometer scale global models that will complement other modeling approaches, but again, and so they will provide, of course, local information, but of course it's important that we democratize and operationalize these tools. And again, we should be able to provide information to each citizen of the world. And this information is not just numerical information, it's information with analysis and with discussion. Here is an example of the different variables that we need to measure. They deal with the hydrological cycle, with the energy balance, with the carbon cycle, biosphere, and with composition and transport. Again, issue associated with atmospheric chemistry or air quality and climate are two sides of the same coin. Models will change also as technology evolves. We're going to go to kilometer scale climate models, but even to higher resolution with large eddy simulation, for example. The need, of course, of using artificial intelligence to downscale essentially what the models are providing, have some regional nesting, and finally try to get information that will help actionable climate science. So a lot of work for both the observation people and for the modeling people. Challenge number 3. We will have to live in a warmer world. And when I say a warmer world, I mean a world under climate change. So basically, successful adaptation requires strategies and solutions to deal with, and you have a list here. You know, for example, loss of food security, impact on health. What about climate extremes? How are we going to live with more and more climate extreme and complex risk? Sea level rise and issue around the coast of habitats. Perhaps to have to deal with negative emissions if people want to manipulate climate. Deal also with the irreversible changes that I mentioned, the tipping points that I mentioned a bit earlier. And then, of course, looking at the potential risk, the benefits, the impact of climate intervention if something like that happens. So we have to be ready for these kind of situations. So let me take 2 examples. One is the issue of health, and the other one is a word about climate intervention, which is probably something that will lead to some discussion later on. So how will climate change impact human health? And you see here a graph that shows you different health issues that are related to the disturbances associated with climate change. They involve environmental degradation, extreme heat, severe weather, air pollution, water quality impact, increasing allergies, etc. And you see here a list of diseases that could be more efficient, I mean, more frequent, and where people would be suffering on this. So you see here, by the way, a graphic that shows you also the complexity of the couple climate health system. I mean, it's not just that, oh, it's a bit warmer, I will have a little bit of a problem, you know, waking up in the morning or something. There are a lot of issues that are intertwined. I don't want to get into the detail. I hope you can read a little bit the graph, but at the end, they lead to undernutrition, impact on mental health, cardiovascular disease, respiratory disease, and other one here, well, etc. And this can go through a number of channels. It's not only a problem of the temperature. And so there is now an attempt to really look more and more at those issues, which could become substantial in the future. The second example for the future is climate intervention. Well, you see this kind of graph with a lot of proposed ways of cooling the planet to a certain extent. And in fact, there are essentially 2 ways. One is to reduce the input to the surface of solar energy. And the other one is to let more basically infrared radiation leave the planet or do something about the greenhouse forcing, reducing the greenhouse force. But again, I'm going to, you heard a lot about we have to capture CO2, we have to inject aerosols. I'm not going to talk about all that. I'm going to take the issue of methane that I mentioned earlier, and you see the increase of methane. In fact, the trend is increasing also. It's going faster and faster. And frankly, we don't know too much about. In fact, it's an important issue, methane. Why? Well, if you look here at the temperature anomaly that is predicted under scenario 4.5, you can see on the left what happens with the CO2, which is essentially the green color, and the methane contribution is in blue. And you see that in the next 50 years, 60 years, the methane under a scenario that has been adopted here, SSP 2.5, the methane contribution for the warming is important. So what can we do about it if we really want to do? Well, first of all, we have to recognize where the sources are of methane. And here is a list of sources. Wetlands and other natural sources are very large. Secondly, agriculture. Then biomass and biofuel burning. Then waste, and also you see to large effect the fossil fuel. So natural emissions are large, wetlands and other, but the emissions might be climate dependent. If the temperature increases, the natural emissions will be larger. So they're not really natural anymore. They're also natural, but affected by human activities. So nobody knows exactly how to reduce those emissions. But there are now some people who are considering geoengineering to slow down the methane growth, either by reducing the emissions somehow, or by increasing surface methane consumption. And you see there, and don't have time to go in detail, but several mechanisms that are proposed to basically eat up methane from the atmosphere. Or you could also increase the loss, the atmospheric loss process by chemistry, destroy methane in the air by increasing the OH radical, which is basically the detergent of the atmosphere. And you can do that by geoengineering, but it will affect a lot of the pollutant at the same time. And so all that has a lot of risk that to be carefully determined and discussed, like in the geoengineering concept should be discussed and not left in the hands of a few, large companies that would just do it for the government. There is no international agreement between countries on doing or not doing geoengineering. And so it's not very expensive to do geoengineering. It could be done pretty much by a country, by strong industry who think they can make a lot of money out of that. But the consequence for other parts of the world or for other people of the world need to be clearly assessed. Challenge number 4. We need actionable climate information at the regional scale, and in fact, more than climate information. We need to essentially improve the regional projection and prediction. We need to basically try to integrate all this in a broad sense. And I think really the Earth system model of the future need to a large extent to be regional Earth system model in order to account for the interaction between meteorology, air quality, hydrology, biology, and their perturbation by industrial, agricultural, and urban development. That's where the connection with society is the most likely to happen. The climate community needs to move regionally and not just believe, I mean, climate is a global problem, but the perception, the effect of climate are going to be local and regional. And so we need to do that. Now, I'm going to take an example of a regional or local problem, and I'm getting into air quality a little bit, and in particular, in an urban area, which we discuss here. This is basically the increase in, well, of the share of the population in urban area between 1960 and 2021. Over 4 billion people live now in urban areas globally. And so if you are an urban planner and you deal with this question, you start to have to look at a very complex system. And you can see a lot of the issues, climate, ecology, energy, pollution, health, education, equity, community, security, sustainability, growth, employment, productivity, management, governments, transport, etc., etc. We don't have time to look into that, but it's a highly interactive system with a lot of issue associated not only with the physical environmental system, but with the human environmental system. The city is probably the place where those connections are the most important. So I just want to talk a little bit about air pollution because this is one of the topics of this conference. It's a global threat happening in many regions of the world, even though it happens mostly in urban area. It is related to industrial development and industrial pollution, but we have new sources of air pollution today, in particular wildfires. It was very important a year ago in Canada. You see two pictures of New York a day apart. It's becoming important in Brazil with the dryness of the Amazon and the number of fires that are more and more important. So the issue becomes more and more crucial, not only in the northern hemisphere, but also in the southern hemisphere and also in the tropics. And so we need for air pollution to start having not only small air quality prediction system, we need to have a good observing system. And I just want to show you some recent progress. This is June 2024, and this is a new satellite, which is a geostationary satellite. So it's a satellite that turns around the Earth at the same speed as the Earth rotation. So if you sit in the US, the satellite is always above your head, doesn't move relative to yourself, and it can monitor the diurnal evolution, hour by hour, of the air pollution. The satellite is at 36 kilometers, so you need very good instrumentation to see things at high resolution, but those satellites now see things at about 4 or 5 kilometer resolution. You see here nitrogen oxide. This is the second geostationary satellite for atmospheric composition. The first one was launched by Korean. It's called GEMS, still there. This is the American version of it. It's called Tempo. There will be a European version, but what is missing is a South American geostationary satellite. And by the way, there is also a need to put an African geostationary satellite. So the Southern Hemisphere should be able to have space monitoring. I cannot resist to show you an example of the diurnal variation of a chemical compound. This is formaldehyde. Nobody probably cares here much about formaldehyde, but I do, because we haven't been talking much about the organic chemistry, the volatile organic compounds that are produced by humans or by nature, trees, vegetation, but also industry, residential area, and those VOCs, as we call them, get transformed, for example, into formaldehyde. And this is over the US with this new satellite measured in June 24, the diurnal evolution hour by hour of the presence of these compounds. This example to show you that technology will help us to do some monitoring. What will also happen is a higher resolution of the models that will really see what happens street by street in the urban area. I don't want to go too much in detail. In fact, I'm going to pass this a bit, but I'm going to show you one example here for Hong Kong. You see at the top three level, this is nitric acid, nitrogen oxide, and in the lower part, this is ozone. And the resolution of the mall on the left is 900 meters, in the middle is 100 meters, and on the right-hand side, it's 30 meters. So we can now basically simulate the chemical composition at a resolution of maybe 10 to 50 meters, and we can see the complexity of a system. We can add the buildings, we can have the street canyon and try to represent, and finally to tell you what are the part of the city that are highly polluted, usually the poor region of the city. So the question of environmental justice, the exposure of the poor population and so on, all these questions can be addressed by tools like that. And of course, the health issue is important. And here we need really to start working much more efficiently with the health community. You see on the left, essentially, what we call the exposure analytics. On the right, the health analytics. There is a need to bring together different tools, some coming from our community, others coming from the medical community. And frankly, we haven't seen enough of this interaction between the two communities. Now, I showed you an example on health, in particular in urban areas, but I would like to say that as we start better understand the dynamics of the urban complex system, we need to get there also a very interdisciplinary approach, a very holistic approach. You can see here, for example, this is for the Great Bay Area, so near Hong Kong, starting with ecological degradation, having satellite sensors, going to finally and the determination of environmental parameters, trying to, this is for climate, that's not for air quality, but trying to provide information by fusing data and model, and also, of course, to involve the population in the discussion. And so the need to engage stakeholders, and you have to do it at different levels. They can be contractual, they can be consultative, they can be collaborative, they can be collegial. They can deal with different size, with different objectives, different types of relationship, different involvement. I think we need to better discuss this. How are we going to involve citizens in the process, in particular in urban areas? It's easy to say that we're going to do it. It's easy to say that a lot of stakeholders around, but when you try to say, could you tell me the names? It starts to be very theoretical. And when you organize a meeting with them, you don't see them coming. So we haven't really succeeded to create today sufficiently well the relation between researchers and stakeholders. And we need to really think about it. Finally, the challenge number 5. All that I mentioned requires a transformation of society. So there is, of course, a dramatic and urgent need for climate mitigation. to limit global warming, and that require already a large societal transformation. But we also have to build resilience that will be key for adaptation to amplified impact and risk for people and for ecosystem. So we need openness, we need transparency, we need equity, and we need climate information for all, so that we ensure or we facilitate some climate justice. So climate change is interlinked, of course, with other threats. We should not forget that, should not be too climate-centric. I mentioned conflict, I mentioned other population growth, but I could also mention food shortage in parts of the world and population displacement that might be triggered from economic reasons, but also from climate change and sometimes from both underrelated or completely related. So thinking about societal transformation is something that cannot be done by the physical climate community alone, but it's very important that this community contribute to this kind of discussion that needs to happen. And Climapolis is a good example, I think, of an attempt to address this problem. We have been studying a lot with physical aspect. The program, the project evolves now in here with much more direction, as I highlighted them. Participation, citizen science, social science, a lot of different aspects that need to be integrated, health issue, and many others. Low, because clearly we will need frameworks to do those changes. And so I wish you best luck for the Brazilian contribution of Climapolis that is really now taking off. And I know that you're going to do a great job because we have seen how you're working in the first phase. So congratulations to all of you. And I'm now ready to answer your questions. Thank you.
Okay, so, A tela. Ah, tá, sim, peraí, vamos tentar se vai dar certo aqui. Sim. Very nice. So we have a very nice background now. Okay, Guy, thank you very much. It's a really inspiring and invigorating talk to continue our work within INCT Climapolis. And I thought it was very inspiring also to think maybe about the geoengineering aspects. So I have a question regarding that, but I will open to the public first to ask some questions. So we have first Nico and then Katrin. Oops. You want to come here and ask a question? The microphone. Katrin. Yeah.
Yeah, thank you very much for the talk. It's always inspiring. And I was lucky enough when I was in Hamburg working with you to have similar talks every time we would go for lunch. So it taught me a lot to think in a more very open way and pick different things. And for that, I'm very, very grateful. I want to pick your brains a bit when you challenge in the sense of the regional Earth system models. Because we are going to the kilometer scale, we may not need the regional Earth system models because that will be addressed. We are going to pass the semi-class type downscaling to Cordex type for regional. The main issue is because we still don't have the necessary infrastructure and sometimes even the capacity in some regions of the world to do that. Even today, if we go to that type. So because we are going to have global kilometer scale models, we may not need that. However, I agree that the information needs to be regionalized because climate change is still a very mystic thing for the majority of people. 1.5 degree warming means nothing for people who are experiencing, it's going to be nice to have a little bit more warm. Projections in the end of the century for whatever is going to happen, if you talk to the farmer, they are concerned about what's going to happen the next season because that's where they're concerned about their planting. So the regionalized aspect is where you bring those issues back to life to those people living in those places. So it is that contrast of the technology that we need to regionalize rather than the information that needs to be local. So it's a global problem, but local impact. So just to pick your brains on that discussion.
Okay, so my answer is, in other words, I agree with you that people need regional, even local climate information. It doesn't really matter if the model is regional or global. However, the current global climate models work with typically 50-kilometer resolution. Some may go 20, but I don't think that really happens. And so you can go on and hope that, yes, you might have stronger computers or put computers together so that you could do a 1-kilometer resolution global model. And in that case, you don't need regional model. But the challenge to reach that level is enormous, and it will take years and years. You know, when I was in China 2 weeks ago or 3 weeks ago, I heard a presentation of a Chinese scientist who said China is going to build a mall global that will have a zooming capability in China. We will do a climate model regionally at 10-meter resolution. So I want to see it, and we have the computers to do it. Well, I want to see if it really happens. In the meantime, I think that it would be wise to couple with global models some regional zooming capability in the global model, so have a grid that is focusing, or to embed in the global model a regional model. The advantage of the regional model is that it can include many more processes than you can put in the global model. And so it's a technological question. It's based on the computer capability that is available for you. But I think that if we say, oh, let's wait until we go to a 1-kilometer resolution with very little more just the physical equations of the Navier-Stokes equation for the atmosphere and for the ocean, we need to have much more information about other aspects, carbon cycle, nitrogen cycle, the hydrology, all that, just the urban specificity and so on. It'd be very difficult to put that in a global model right now, but it's a technological approach. So I agree with you, in fact.
Catherine?
Okay, Thanks, Guy, for yet another inspiring talk. I have two very different, yeah, I can also. Does that help? I have two very different questions. One is on this downscaling. So when we were talking about urban planning and adaptation a lot, and as an urban planner or an architect, if you have a model that works on a kilometer scale or even a 10-meter scale, that's not good enough. So we were trying in a research project in Freiburg to substitute physical downscaling with the help of AI. So we're using physical modeling data and then training AI with local data to get meter-wise information on heat, water, and storm for the city of Freiburg as a basic science research project. And it worked well for heat. I mean, I don't know at the end, so that's what the colleagues told me. It did work well for heat. It didn't work so well for water because you cannot simulate the city so well with all the inclinations and stuff and cannot train the AI properly. And storm is always complicated, basically. And they have hope to improve that. But like, what's your personal opinion on that role of AI in breaking down the data and making it work also for urban planning decisions? Because we need them urgently. And yeah.
Yeah, I think this is an excellent question. And I say that I should have been talking a little bit about it, and I didn't. I talked about the technological revolution. The third one was really about introducing AI, but I didn't say it explicitly. So I believe that, yes, you have to be careful what you do with AI, but there are things that work very well and that should be doing very well. For example, here, in the last 2 or 3 days, we have been talking about exactly that for air quality, because we have another project called Qualaria that's done with people, also Meteo AI. So it's a small company that is really working on applying artificial intelligence for downscaling. And so this is probably the best way. It's that you use the model that gives you the background, the course view, and then you start to do downscaling by training your system to understand what creates the variability from the course situation. So completely interesting question. My answer is yes, yes, yes.
Okay. So maybe to add to that, so one thing that we found out is also what Peter Fröder said the other day: if you put crap in, you get crap out. So we were really thinking about with which information to train the AI. And we went with a LiDAR scanner through Freiburg. And if you go through the rich neighborhoods with low density and train the AI with only this information, the predictions for the higher density, poorer areas are crap. So there's a lot of justice implications in how you do that, and you can do it, yeah, well or not so well. So it's really also a bit of a dangerous issue, and you gotta be really sure that you train the AI with good data.
And in fact, for air quality, we have a bit this problem in South America because we don't have a lot of information. And so our idea here is to train the model in different regions, because the physics is the same. The conditions are not necessarily the same, but we cover a lot of different conditions. What is, of course, where you have to be careful is to look at extreme events with AI, because they might not have happened before. And so you train your system, and the system does not never encounter a new situation. So we're working on that, and it is fascinating. And we do it with our friends from Meteo AI, with Fatima and other people. We're trying to do that for Sao Paulo, for air quality, and they do it also for climate. So yeah, it's a, but I agree, junk in, junk out. So you have to be, the most important thing is to train the system the best possible.
Okay, thanks. And the second question, super different. Once you told me that you also worked as a politician at the city scale, right? Quite a while ago, maybe, I don't know. What's your advice on this democracy crisis that we are facing and decision-making in cities? What do you think are the most important factors to, despite all these challenges, move on in decision-making at the city scale from a political perspective?
Yeah, I think that it would be good for cities. I don't know, of course, how they would work in a large city like Sao Paulo, but in cities to have neighborhoods groups, council. Now, these groups might not be elected, they might be not democratically representative, but they are an important voice to express a number of concerns when those concerns exist. And I believe that when you are involved in a project, can be urbanistic project, can be creating a road or in a new line of subway or something, that you have consultation with those groups, and that you try to create around this group connection with the people who live in the neighborhood. So it has to be done at the neighborhood level. And of course, it's not without problems because, as I said, those groups are not necessarily representative. The more interested people, maybe the more opposition people will coalesce around those groups, and the other people who are not saying anything but might have a different point of view. Those groups might not be sufficiently informed, but you need to have this dialogue. And so having neighborhoods group, maybe that exists in many cities now, it's a way for you to get the information. But at the end, the decision has to be made by the people elected. And if they mess up, they're not going to be re-elected later on. So that's why democracy at the urban scale is so important. Much more important probably than at the national scale very often for what concerns individuals. So the local democracy, very, very important.
Any more questions? We still have time. Anna.
Oh, thank you, Guy, I don't, I can't target your presentation. It's inspiring, but I'm feeling afraid. Not inspiring, but give me afraid. Because I think it's a challenge situation for the future. It's not easy to take into account seriously as it is needed to be. It's not a question, but it's a comment regarding this debate between you and Catherine regarding local democracy. Thinking on these 5 challenges, I'm very concerned about transforming society and how can we deal with the warming world. So maybe our perception of democracy should be transformed either, because for neighborhoods organization
of their environment. They have much better perception of the consequence of some decisions that are taken. And yes, it is the role of the leadership to have plans, but plans cannot be done in vacuum. You have to do your plan. You have to have your objectives, political objectives, clearly. These objectives need to be known at the time of the election so that people can choose what objective they want to do. They have to give a mandate to the people in charge to organize it, but the democracy, I think, is a continuous process. It's not once every 4 years or 5 years that you decide something, because situation evolved, the perception evolved, and so there need to be a standing dialogue, and that needs to be organized so that it is solid. There is mechanism to account for what's coming from the bottom up, and at the end, the top has the responsibility of informing, maybe contradictory sometimes, about a problem. I mean, when if you organize, I don't know, some project in your city, there might be 2-3 points of view. Those 2-3 points of view, one might be the one from the mayor or from the leader of the city, and the other one might be the people, and then there might be a third one. And those have to be explained contradictory and discussed, and that takes a lot of time and a lot of effort. But that's how you create consensus at the end. Not always. Sometimes you have to make a decision that's not a consensus decision, because as you said, we know that climate is going to change. We know that they're going to have a number of questions. That's what the science is saying. And maybe there is not that perception by the population. I mean, you know, if you take the US election, I'm not sure that the president has been elected on the climate program, right? But the people who have voted for him either don't know about it and they should be informed, or they consider it's less important than other priorities. And that's the political game. That's the political life. And that's why people are fighting for a certain number of objectives. So it's complex and it needs leadership. I agree. But the leadership is not dictated.
My name is Paulo Manta. I work in the São Paulo City Hall. My English is no good, but I want to ask a paradigmatic question. Is there hope for example, for Bangladesh? Bangladesh is a poor country. It has not so many to do with the global warming, but the global north won't accept to decrease its life level. And we know maybe the world won't accept so many emissions. We will have a war between North and South global. How will be the management of the world?
Yeah. So let me say the following. You have a number of relatively poor countries that will be hit strongly by, for example, sea level rise, by climate change. The weight of these countries in the international negotiation, even though officially they have one vote, probably like everybody else, but the weight, the intellectual weight is relatively limited because the game happens between 5 or 6 countries. And including industry, including the forces that are behind those countries. So it seems to me that there is very little hope on the political side that those countries really support it, even though we're going to be hit. And the same thing for the islands in the middle of the Pacific. It's a small island. The island might disappear. Does this really affect the big nation? Not really, right? So, too bad. So, one way I think that perhaps we should think about this, and this is something for us, is really the importance of developing partnerships between scientists in these regions. In other words, we need to support those people and we need to help them develop some capability, intellectual capability, scientific capability, technical capability, monitoring capability, so that they have also the training, the mentoring, and so on, so that their voice can be better heard. And this is maybe something we can be doing. Now, all that being said, we talk about environmental justice. This is a good example where environmental justice should be implemented. So it is also a political situation, a political agenda, and we need to support that, I think.
Any more questions? Renato.
Just one brief but not easy question. Is your challenge 3? Is how to live in a warmer world. So for coincidence, we propose the title of the next architectural biennale is Architectures for an Overheated World. So it's the same, and but it's architecture in our case. So when we list the items for successful adaptation, many of them is unlikely to be achieving this space that we are ongoing now. So yes, this is a political question. I think we have different answers from different parts of the world. Of course, from a bottom up in global north, where the citizenship is nationally recognized rights that people here in the south don't have. So the national reference is very important, maybe much important for us than in global north. So there is some difference in this, but we are doing, trying to learn how to shift for a new kind of dialogue with communities, bottom-up process. But climate change is something that is scientifically explained. You can feel, but you have different explanations, different narratives, as you know. And the negationism is one very good narrative that attracts a lot of people. So people are voting in Trump not because they deny climate change, but they need coal for work, miners, and this is what they propose. So this, I remember talking in January in Hamburg. You address an item is the cultural discussion on negationism, denials of the climate change. So today and this morning, when we received representatives of the community of tourism and also the chief of the cabinet of the local authority, at the end, what they emerged from that discussion, that what attracted them to receive us and what learn with them and what they learn with this was this interchange. We are not teaching, but we are not only listening, we are talking, we are debating. So, and this is requires maybe another framework for political future in the world.
Yeah, I don't know what I can say because I agree it's a difficult issue. You don't want to have the countries that are developing themselves not too developed in order to preserve the environment, while other countries have been developing themselves and will develop themselves. But you could help those countries to find new ways of developing themselves that are less emitters of CO2 and other gases. I think, you know, what struck me even when I was in China, I mean, this country was a real developing country 10 years, 20 years ago. They are developing themselves, and they did develop themselves first, like the West or the North, or, you know, cars everywhere, buildings everywhere. So they just follow the Western or the Northern system. And they got air pollution. They were dying almost. They get climate change on the way. And they realized that they had to change. And so they move, in this case, and you can say it's not the right solution, but at least they're trying something. They go to electric cars and they do a lot of things. You know what? When I was in my hotel, I had a note on the table that says, "This is empty dish months." In other words, rather than putting so much on your plate and leaving everything, put less and eat everything. Well, it's a small thing. So what I'm saying is that we need to find new ways of developing ourselves. If you take Africa, I think, which is the continent that will be on the agenda very, very strongly in the next decades. I mean, these people will want to develop themselves. So what do we want? Cars, buildings, the same as the West, and get a huge pollution? Or can we think of a type of development that is different? That's a transformation of the society that I mentioned. So we need to talk about that. We don't know what it means. That's why I didn't want to talk much about it, because I don't know what it means. But I would like to discuss this with the appropriate people, including the population and the people with different culture, because the development should not be the same everywhere in the world.
Guy, okay, a last question from my side. Yes, exactly. So, okay, I like to compare geoengineering to a person that has a curable disease, and the doctors give him or her morphine and say, look, just because the person feels pain, okay? And they say, okay, you take the morphine the rest of their life and you will not feel pain anymore. But they do not think about looking what is the underlying disease and cure that disease. So this is a bit what is my feeling about geoengineering. But maybe it can be an additional measure to cool the earth until CO2 actually starts to decrease. I'm not sure, but I was wondering, you showed the idea of reducing methane. And when we look at the sources that you showed of methane and why they are increasing, it makes me wonder if it wouldn't make more sense to stick to the CO2, because methane has a very short lifetime compared to CO2, like 12 years or so. And the problem of methane will be solved faster, let's say. If we reduce CO2 and we get cooler temperatures, then the whole natural wetlands and so on, natural sources will already reduce their emissions of methane. And this would already lead indirectly to a reduction of methane. What do you think about that?
Okay, you have several questions, in fact, in your question. Geoengineering in general. Think about it. It is essentially a proposal from the military industrial complex. It is not something that the people have proposed. Large companies believe that they can make money out of it, and the military believe that they can use this also as a weapon. I'll give you an example. In 1960 or so, in the 60s, the US had a plan to do geoengineering by creating an ozone hole over Russia. Yes. By injecting bromine from high altitude airplane over the Soviet Union. But why? Because they said, we do that, the solar radiation will be stronger and will burn the farming, the culture from the farming, and the Russian will starve and Russia will get nicer. So there was this. And it was proposed by the head of the science, research group, Wexler, and it was studied at Caltech. The question was, how much bromine should we inject? They didn't do it because they suddenly realized that this hole could move away and pass over the US. But a lot of companies probably were ready to do it if they got good money for it. So it is something that is not completely disconnected with the industrial system and with the military system. Number one. Number two, it's a way of telling us that don't worry about climate change, technology will solve it. Just relax. We'll just put a little bit of aerosol and everything will be okay. The trouble is that if we do that, the level of CO2 will be high, the ocean will be absorbing a lot of carbon, it will affect the biosphere, it will affect the food chain, and suddenly we will have nothing to eat. And we all I said, gosh, we should have thought about it. So it is an approach that's psychologically a bit dangerous to adopt. Now, there are different types of geoengineering. I mean, if you capture CO2, you suck CO2, maybe you will not have a lot of secondary effect, although if you suck it and you take it away, you have to put it somewhere. So people put it in the ground, okay, maybe 1,000 years, it will stay there, and then suddenly, up, it will go back in the atmosphere. So we don't know. Putting aerosols, well, maybe, but how is the weather going to change at the other side of the world? We don't know exactly. And we can trust the models, but, you know, so it is finally a problem that is touching us as society as a very difficult issue with consequences. You know, I can do geoengineering without any problem if it's in my model. But I don't want to do it on the Earth because the Earth, my model, if I trash it, I have a model. But the Earth, I don't have another Earth. So I would be very, very cautious. Now, you had a question about methane. Don't underestimate the role of methane in the warming. And in particular, you know, if you look at the next 50 years, methane and ozone change might be at the end at least 50% of the warming. The CO2 problem will come later on as the dominant problem. So you have to do something about CO2. Don't let me, I mean, I'm not saying we should not do anything on CO2 and just do it on methane. I was just showing you that in the case of methane, where the lifetime is only 10 years and CO2 is much longer, one could potentially do something, but again, it's entering a dangerous era, a dangerous way of solving a problem that maybe should be solved in a different way.
Okay, thank you, Guy. It was a very complete answer to all my questions. Okay, so we are closing the session for today. I want to thank you again, Guy, for your very interesting talk that will give us all material to think about a long time, I guess. And well, it's almost 8 o'clock, so we are leaving the conference today with something to think about and a very nice picture in the background. Thank you for that too. Thank you very much.
Thank you.